Today, we're going to look at Gauss Markov Theorem. So, what does Gauss Markov Theorem says? Let me just write the few points. An OLS estimator C beta 2 hat is said to be blue. What do you mean by blue? Blue means best linear unbiased estimate. Best linear unbiased estimate of beta 2 if following holds. If following holds. Please make notes alongside me. One, it is a linear function. So it's a linear function of a random variable such as a dependent variable, capital Y, in the regression function. So it is a linear function. It is linear. That is a linear function of a random variable such as a dependent variable Y in the regression model, right? So I'll I'll explain all this. Let me just write few points first. Second, it is unbiased. Unbiased means what? E of beta 2 hat is equal to beta 2. That is, it is unbiased. Third, it has a minimum variance in the class of all linear unbiased estimates, right? So there can be other unbiased estimates also, right? They're linear also. But this OLS estimator has the least variance. That is what it is. It has it has a minimum variance in the class of all such linear unbiased estimates, right? In the class of all such linear unbiased estimators. So these are the three main points. Let me just start by proving it is unbiased first. So guys, I will be doing the a proof for unbiasedness and the variance again. Although I have used Christopher Degerty, uh, but the way Gujarati proves it looks more natural to me. I mean, although the proofs are more or less same, but still I want to do it once more. So I'll be doing this in two parts. So for Gauss Markov theorem, I'll be doing it in two parts. So I'll be proving unbiasedness and the variance in this part. And in the next part, I will prove that some other estimator will have a larger variance as compared to the OLS estimator. So OLS estimator is the best estimator. That is what it is, right? So this is in two parts. So I hope we remember this very well, that beta 2 hat we have already derived, that is summation of small xi small yi upon summation of small xi square. That is what it is. And let me write this ki as small xi upon summation of small xi square, right? So I can write, and this ki is just dependent upon xi's, so and xi's are non-stochastic, so even ki is non-stochastic. Beta 2 hat then could be written as summation of ki yi. Now why am I writing like this? Beta, you can write like this thing. This is just small y, which is this yi minus y bar. So it is summation of ki capital Yi minus y bar summation of ki, right? Now the point is that we'll be proving just in a meanwhile that summation of ki is equal to 0. That is what we're going to prove, and from there you will straight away get this summation of ki capital Yi. And the moment you write like this, that is your beta 2 hat is summation of ki capital Yi. So you can say that beta 2 hat is a linear estimator of uh, of uh, of this thing. Is a linear estimator is a linear estimator of y, right? Actually, it is a weighted average of yi with ki serving as weights. So it's a linear estimator, first thing. Then there are a few properties of KIs which you can write. Hmm. Properties of KI. One, since xi is assumed to be non-stochastic, ki is only dependent upon xi, so ki is also assumed to be non-stochastic. KIs are also non-stochastic, right? Second, Beta, what is summation of ki? Summation of ki is what? Summation of, so it is summation of small xi upon summation of this thing. So this is equal to 0. Why? Because this is sum of deviations from mean. Sum of deviations from mean, one thing, right? And this guy, your summation of ki square. Since you have done the other proof as well, so this doesn't seem very different to you, but this is useful. I mean, the way Gujarati has written it, it seems more intuitive. Xi summation of xi upon summation of small xi ka square. So this is summation of small xi square upon summation of small xi square square. So that is 1 upon summation of small xi square, right? And fourth, summation of ki small xi. Xi minus x bar ki xi minus x bar summation of ki. But summation of ki is equal to 0. That's what you have seen, right? So what is it that you know till now? That summation of ki small xi is equal to summation of ki capital Xi. Very well, right? Okay. Now what else you can do? That is, this is what then? Xi summation of xi square into xi. है ना? This thing. So this thing becomes what? Summation of small xi square upon summation of small xi square. So that is equal to 1. Right, beta? So summation of ki small xi is equal to summation of ki capital Xi. Both are equal to 1. Both are equal to 1. So these are the four properties you should remember. And since you have already shown that summation of ki is equal to 0, so you know that beta 2 hat could be written as summation of ki capital yi as well. Right? Summation of ki capital yi as well. Right, beta? Okay. Now you go back to the model which you have. That is yi equals to beta 1 plus beta 2 xi plus ui. Fair enough. So this is what you have. Beta 2 hat is what? Summation of ki capital yi. In place of capital yi, you have what? Beta 1 plus beta 2 xi plus ui. Plus ki ui. हाँ beta. What is summation of ki? 0. Summation of ki xi? 1. You have just seen this. So beta 2 hat is what? Beta 2 plus summation of ki ui. You can just put the expectation sign. E of beta 2 hat. Now this is a constant. This will be just beta 2. Summation of ki's are non-stochastic, so they will come out of the expectation sign. E of ui. But E of ui is 0. E of ui is 0. So this is the assumption of your model. That is, on an average, the error terms are going to be 0. So what is it that you have shown? That E of beta 2 hat is equal to beta 2. That is, beta 2 hat is unbiased. This is an unbiased estimator. So this is what you have shown. This is what you have shown. That is, it is unbiased. E of beta 2 hat is equal to beta 2. That is what you have shown, that this is unbiased, and it is linear as well. Now about this guy, it has a minimum variance. So let's just start proving that as well. Let us just start proving that as well. Well, minimum variance I'll prove in the another recording. Let me just find out the variance first. Variance of beta 2 hat would be what? E of beta 2 hat minus E of beta 2 hat ka whole square. I hope you know this, that what is, sorry, variance of x is E of x minus x bar ka whole square. That's what you have. E of x minus x bar ka whole square. So E of beta 2 hat minus E of beta 2 hat ka whole square. हाँ बेटा. And what is E of beta 2 hat? Beta 2. Okay. Now you go back to the proof which you have done. This is the proof which you had. Beta 2 hat minus beta 2. How can you write this? Summation of KIUI. Okay. Beta, how do you write this guy? Your K1, sorry. How do you write K1 U1 plus K2 U2 का square? K1 square U1 square plus K2 square U2 square plus 2K1 K2 U1 U2. हाँ बेटा. Okay. So, and if you wanted to write this way, if you wanted to put the expectation here, how will this come out to be? K1 square. You don't have to write this. I'm just explaining you this. E of u and K1 square will come out of the expectation because K1 being non-stochastic, depending only on x's, and x is being non-stochastic. K2 square coming out of the expectation. 2K1 K2 coming out of the expectation. What is E of u1 square? Sigma square. Head homoscedasticity assumption. U2 square, sigma square. What is E of u1 u2? 0. No autocorrelation assumption, right? No autocorrelation assumption. This is what we're going to use. So all the cross product terms you will see, they will come out to be 0. That's what we're going to see out here. So basically you have K1 U1 plus K2 U2 and so on to K and UN ka whole square. K1 K2 U1 U2 and so on to 2Kn minus 1 Kn UN minus 1 UN. You put the expectation. E of UN square, and then all of these cross product terms are there. this. Beta, this is what? Sigma square, sigma square, sigma square. What is this? 0, 0. Why? Because E of ui square is equal to sigma square, that is homoscedasticity assumption. And E of ui uj is equal to 0, no autocorrelation assumption. No autocorrelation assumption. So basically what you have, that all the cross product terms, they are equal to 0, right? All the cross product terms, they are 0. So you have what, beta? You have this k1 square sigma square plus k2 square sigma square and so on to kn square sigma square plus 0 plus so on to 0. All the cross product terms are 0. So you have sigma square k1 square plus k2 square and so on to kn square. So basically what do you have? Sigma square common summation of ki square. That's what it is. And what is summation of ki square? You have just proved it here. This thing 1 upon summation of small xi square. So this is what your variance of beta 2 hat looks like. So variance of beta 2 hat is sigma square upon summation of small xi square. This is what we have. So in this part, I'm doing this. In the next part, I do the second part of the Gauss Markov theorem. So in case if somebody asks you for maybe a 15 marker question or a 20 marker question, you will have to prove unbiasedness, you will have to find out the variance, and then you will have to show that if you use any other linear unbiased estimate apart from the OLS estimate, its variance is going to be more or would be equal to this OLS estimator only. So in case if that is equal, that means that indeed is the same OLS estimator only, and if that is going to be more, then you know that the OLS estimator has the minimum variance, right? Okay, thank you, Beta.